So this is some work that I did with these fine gentlemen while I was at Indiana University. And it's all about converting between simply typed and typed indexed versions of the same data type. And so the story of how we came to this research begins, like so many stories, with a dream. And so Ryan really thought, we should be teaching our students about parallelism. The free lunch is over, multi-cores are here. Our students really need to be able to design and implement parallel algorithms, parallel programs. And so if you've seen me speak at one of these things before, it's probably been on this thing called Accelerate. It's this embedded language for data parallel arrays, which I've been working on for a few years now. And so we thought, great, well maybe we can have them hack on this Accelerate thing. We can use this as a vehicle to teach them about data parallelism and programming GPUs, for example. With our respective backgrounds, we should be more than capable of doing this, right? But we started to run into some problems, right? So Accelerate is still very much a research project, and part of that is that it makes extensive use of type indexed data types throughout its compiler pipeline. And so that's fine, but it's something that we needed to keep in mind if we wanted to have our students working on this, because it's the fancy types can make working with it a little bit trickier, right? So as an example of something that might go wrong would be if you tried to write a program like this. And so type class deriving is this great feature of Haskell, right? But if we ask GHC to derive a read instance, say, on a type indexed GADT, then it will very politely say, no, I'm sorry, I can't do that. And so we thought, maybe there's something we can do about this. And so this forms our jumping off point, right? This was our original motivation, or frustration perhaps, in working with GADTs, where we started to look into this work. And so to help illustrate how this can become a problem, we'll start with our sort of canonical example of a regular polymorphic list here. It has the usual constructors, nil and cons. And so this is the kind of thing that I mean when I talk about a simply typed data type, or an ADT. Right? But our friend list here has a problem. Right? So if we ask for the first element of a list, or the head of a list, that's empty, then we just get a runtime error. Our program fails at runtime, and there's nothing that our compiler did to try and warn us that this might happen. Instead, if we wanted more static guarantees that this wouldn't happen, we could move to a type indexed representation, or our familiar VEC example, where our extra type parameter n here is going to observe at the type level the length of our list. So our nil constructor now says this is a VEC of 0 length, and then every time we cons on an element, we observe at the type level that our length increases by 1. Right? And so in this way, we can write our head function that says, statically, you must give me a VEC of at least one element. And we can get our compiler, our type checker, to enforce this at compile time rather than leading to a runtime error. And so we can continue with this idea and push it through the rest of our code base, right? And so having nice type indexed GADTs through our code base is great from a safety perspective because it allows us to catch potential bugs at compilation time rather than leading to runtime errors. But from a development standpoint, this is a little bit more difficult to work with, right? If we have some new feature that we want to implement, it's difficult to make changes to this code base because we now have to provide all of these typing obligations. So things like rapidly prototyping some new idea become more difficult. We still have all of these typing obligations that we need to fulfill in order to compile. As we saw earlier, our fancier data types miss out on some compiler features that our simpler data types enjoy, and maybe this. But we're good computer scientists, right? So we can solve this problem by cheating. So instead of doing everything in our nice, well-typed GADT representation, maybe we can just do our prototyping in a simpler representation. Just use a regular, simply typed ADT. And so the goal here would be, can we quickly determine whether or not this feature is worthwhile? And so if it is, now we can commit to doing all of our nice type indexed representation for that type. And if it's not, we can just throw it away, try something else, and hopefully we haven't wasted too much time. And so as long as we can freely move between these two representations, then we should be able to get this rapid prototyping feature back and test out new changes quickly with our existing code base. But the question now is, have we really just shifted our burden elsewhere? All right, so when we move from our type index GADTs to simply type ADTs, what we're really doing is mostly throwing away all of these type level invariants. Because our type checker has less information now to warn us if we've potentially made a mistake, then this might be a little bit error prone. On the other hand, when we're moving back to our type index GADTs, we need to somehow re-establish all of these type level invariants that were encoded in our GADTs. And this can be a little bit tricky, a little bit difficult sometimes. And so this gets to the core focus of this work. It's moving between these simply typed and typed indexed representations of the same data type. So what are the current options for implementing these conversion functions? Well, actually Haskell has had for a while now the ability to do runtime type checks via the data.typable library. So we can in fact just implement these manually today. But as I mentioned, because these are a little bit tricky, a little bit error prone, then this is adding a large maintenance burden to our code base. And that's maybe not what we want. So a second option, which is in particular relevant for that second phase where we need to re-establish all of these type level invariants, is to use this runtime eval approach. And so this is where we take our simply typed data structure and we just generate a string which represents the GADT version of that data structure. And then we just feed that to GHC, which we've embedded into our program as a library. There's some small overhead for that. Binary sizes are a little bit larger. But it works. It's a little bit slower than the competing approaches, but it's very effective and it's honestly fairly simple to implement. The only thing we had to do was treat all of our nice, richly typed data structures as strings, which is fine. But maybe there's a better option. Maybe there's a third option here. So if we go back to our example, we had regular list and length observed list. So if you're sitting at the back, or if you just squint a little bit, you can see that these are basically the same, right? These have the same recursive structure. And so prior work like ornaments or the dependent interoperability that we heard about yesterday, these frameworks were thinking about, how do we take these two separate data structures and move between them? And so these are very general, very powerful frameworks for moving between two related data structures, but they require you to provide these relations between the two data types, and then they give you something on top of that. And so instead, for our more restricted use case, we would instead prefer something that's more automated. So rather than this, we simply we start with just the type index data type, and we say, Ghostbuster, please, I would like you to erase the type variable n. You can use synthesize mode for this. We'll talk more about what that means later. And just leave type variable a alone. We can keep that in place. That's fine. And so with this, Ghostbuster will generate this new data type vec prime, where type variable n is gone, with constructors nil and cons, as we might expect, as well as the conversion functions for moving between them. So from our pragma here, we've now just automatically generated this new representation and the conversions moving between them. And so with this now, we can think about trying to implement that read instance that for our type index data type that GHC was unable to automatically derive for us. So to do this, we can say, well, just read in, but now read in as the simpler data type that Ghostbuster generated for us. And because this is a regular ADT, GHC is happy to automatically derive the read instance for that for us. We've done no extra work here. And then we use Ghostbuster to convert it into our type index GADT. And this is a type refinement, of course, so we return the result as a maybe. And so we can see Ghostbuster here is helping us to extend the reach of our type class deriving mechanisms. And so, flushed with our success of turning our length observed list into a regular list, we might try and continue erasing type parameters and see if we can go down to our dynamically typed list. Can we just synthesize this type A now? And we'll find out that no, we can't do this, right? If we throw away this information, then we've sort of lost something critical. So instead, Ghostbuster provides this weaker form of type erasure called checked mode. And so in this mode, we can generate our new simpler data type list prime here with constructors nil and cons, where the difference here is that because the type of our element is now existentially quantified, in order to recover that type information later, we need to embed some representation of what that type actually is. And so this will allow us to do dynamic type checks later on and recover our original list. And so with this addition, we can now generate the conversion function to and from our simpler data type. And so this brings us to the core idea of, what's the difference between checked and synthesized mode is really this question of, once you've erased some type information, how do I later recover that information to get back to our original data type? So when we had our length observed list example, and we erased the length in synthesized mode, we can consider the length here as sort of an output of the conversion function. Our vector has some kind of canonical length given by the number of con cells that we used, and we just have to check that that's really the length that we expected. It might be clearer to think about, well, we actually implement this in two steps here, where first we do the conversion, but we keep the length existentially quantified. We just hide it in this extra wrapper. And then in the second step is when we try and expose that length, expose the existential. And so this is the bit that can fail. This is where we have to say, the length is really the length that I expected. But of course, we could choose to keep that existential and just expose it in a limited context like this. Okay, so going back to our example, for our dynamically typed list where we erased in checked mode, the type of our list elements here is really an input of the conversion function. When I want to go back from my dynamically typed list into a regular list, I really have to check that every element of my dynamically typed list really does have the type that I expect. There's no way to kind of hide that under some existential like we did with our length of our vex. And so hopefully this simple example gives you some intuition about what Ghostbuster aims to do. In the paper, there are more examples, of course, including examples of things that don't work, as well as a larger example with a type-safe expression language, which tracks the type of the result as well as the type and scope of free variables at the type level. And we use both checked and synthesized mode simultaneously to erase both type variables here. And then finally, we get into the meat of the paper, where we formalize all of this in terms of a core language. There's the typing rules, all of the ambiguity checking rules for determining when a checked mode or synthesized mode erasure is valid, as well as the proofs for the up and down conversion functions. So in order to test Ghostbuster, we found this website. It was called Hackage. It had some Haskell code on it, so we just downloaded that. And we grabbed all of the GADTs. And about 80%, about 60%, I think it was, have type variables, and 80% of those have type indexed variables. But of the GADTs with type variables, we were able to successfully erase one or more of those and turn these GADTs into a regular ADT about half the time. That's pretty good. In terms of failures at the bottom, the ambiguity check failure, because we're sort of randomly trying all combinations of erasure modes, not all of those are valid. We talk more about in the paper, like what is and is not valid. And then also some unimplemented features in Ghostbuster. We currently don't support all of the features of GADTs in Haskell. In terms of performance, Ghostbuster is really aiming to generate the kind of code that a human would have written anyway. So for this example, we are converting from the type index to simply type representation for a small expression language AST using both checked and synthesized mode. We can see we're on par with the handwritten approach, which is good. And as hinted at earlier, moving back from the simply typed to the type indexed representation. We are faster than the GHC embedded as a library approach and strings. Okay, so in summary, Ghostbuster is a tool for converting between simply typed and typed indexed versions of the same data type, with the aim of helping to incrementalize the costs associated with working with GADTs. Thank you.
We've got plenty of time for questions.
Glepergood Google, why the name?
It started out as we were trying to erase phantom type variables, and then it sort of progressed from there to do more things. Also, what's a cool name? So, easy questions. Good.
Phil Wadler, University of Edinburgh. Listening to all that, I kept thinking of a word that you didn't mention, gradual types. So I wondered if you'd...
Yes. So we talk about that in the paper. There's a nice sort of connection to gradual types where we've taken these type level information and turned them into runtime checks. We also, in the paper, we talk about a nice connection between the representation that we've used, where we have this separate type representation instead of like type dynamic in Haskell, and so that can lead to sort of better asymptotic complexity in some cases of conversion. So, yeah, some details in the paper about that.
Sorry, better than what?
So the example in the paper is if you had like a nested list. So having our separate our representation for the type conversions can be asymptotically better in terms of converting back into the type representation than having this single bundled type dynamic representation. So there's a nice, cute example there.
Hi, Richard Eisenberg from Bryn Mawr College. Your down functions look like magic. In particular, your down vec. It has an n in the result. Oh, look at that.
Yes.
Typable n, okay.
Slightly magic. This is very similar to what Ghostbuster would generate. So one thing that I didn't talk about, you need to compile with a pretty recent version of GHC. 8.2 should be good. Just because of the way that we're using these type representations. But it works, yeah.
Hi, Gergerdi. In the synthesize mode, is there any runtime representation change? Can the downcast be done for free without traversing the data structure if I only use synthesize mode?
So for synthesized mode, there's no sort of embedded type representation. I think that was the first part of your question. But when we do this conversion, we really are copying to a new data structure. So you do have that cost. Like unsafe coerce. No, they're different like data structures. So, yeah.
You indicated that you could do so much more with these unimplemented features. May I know what they are?
Yes. So if we, what's happening? So for the core language, so some things that we don't support are embedded class constraints on constructors. Things like that. So that will hit we can't do that. Certain erasure contexts we don't support. There's some examples of that in the paper of different cases that, aren't supported.
Matthias Goergens. I remember Ola Kielsiow had a paper a while ago about tackless final interpreters, where he went from like basically X expressions, which are mostly untyped, to like something very typed. Does it have any relation to your synthesize?
I'm not familiar with that work.
Okay.
But, we can talk about it after.
Thanks.
Sounds interesting.
Tim Sherd, Portland State. Can you go back to downvec for a second? Because I'm really confused.
Yes.
So that says if I run a vec and I get something of type maybe vec n, so I can't think of any function other than the function that's undefined, maybe undefined, because it says it could be vec 3, it could be vec 7, it could be vec 12. I mean, what vector has all those lengths?
Sorry, no. Sorry, I don't know.
Well, it says I take a vector A, I run it, okay, and if it comes back just something, it can be a vector of any length.
Oh, so if it comes back
So
just...
what value has, vec 3, vec 3, int, vec 7, what value has all those types?
It's sort of this magic thing here, right, where it's like our vec had some length, and you have to tell the type checker that I know what length that is. And so if you can do that, then these types match, and then you get a just something back. So you only get a just answer if you can demonstrate that I know what type this should be. So it's not any type, it's the type that you know, you specified. Is that...
Larry Deal, Portland State. I was wondering if you had any sort of intuition, or if you've already started working on this in sort of an Agdar-Idris-like context where you can not just have values at the index layers, but also function calls. The easy thing to do is to turn the function calls into just propositional equality constraints as extra arguments, but then the question is, like, how well would this technique handle those kind of cases?
You mean like embedded functions in the constructor field?
In the index positions, like in the context of GADTs, it can just be constructors, but if instead you had function calls there.
Yeah, no, I don't think we thought about that, but maybe, yeah, come to me offline. That's interesting. Yeah.
Just one more question. So, John.
Okay, John Hughes, Chalmers and Cubic. So am I right in thinking here that if you were to take up vec of down vec of v, then the compiler would complain that it can't figure out the length? So that if you want to take an svec and then process it as a dependently typed thing, then you probably need to use with vec rather than these operations that you've been talking about.
Yeah, so you might be using with vec in that context if you're not sure or you don't want to demonstrate. But if you do know, like if it's really just a round trip and you expect the same thing to come back, then you could do this and sort of re-expose that type.
Well, how
so
would you do that? How would you tell the type checker? Because you don't know the length of the vec.
Well, I guess no, that depends on your use case. So if you know, you could use this down vec rather than the sort of with vec. So.
Okay, so I'm talking about starting off with a vec whose length you don't know, applying down vec to convert it to the more precise type, manipulating it and then up-vecking it back again.
Yeah, well, I guess if you still have that type variable in scope, you can still, it's still this same type variable. I don't know what it is, but it's the same. You could do that, I guess.
Okay, I'll ask you that.
Okay, yeah, maybe we take it offline.
Anyway, let's thank the speaker again.